Voyager 2's exit from the interstellar bubble was not without surprises. According to the data, the bubble was found to be very leaky. This is because the material from the solar bubble was discovered in interstellar space. Voyager 1 had found signs of a leaky bubble as well. In that instance, however, interstellar material was found streaming into the bubble, and this is the opposite of what Voyager 2 discovered. The new findings confirm that the leakiness of the heliopause, spotted in two very different parts of the heliosphere, is not a rare characteristic of the bubble, although there is still no real explanation for what's causing it. Before the Voyager missions, scientists predicted that the solar bubble just sort of dissolved into interstellar space as you ventured farther and farther from the Sun. Data from Voyager 2 seems to confirm this fact. The craft's plasma wave instrument ended up measuring plasma densities that were very much on par with what Voyager 1 detected. Because solar plasma is so hot and interstellar plasma is incredibly cold, the density of plasma jumps up by a factor between 20 and 50 as you cross the border. Scientists note that this characteristic of fluids forms very sharp boundaries. They were especially surprised that both Voyagers crossed the heliopause at the same relative distances. Previous models heavily predicted that heightened solar activity during Voyager 1's crossing in 2012 should have pushed the bubble's boundary farther out. A period of low solar activity should have pulled the heliopause back a bit during Voyager 2's crossing, which came later. The fact that both spacecraft left the solar system at pretty much the same distance, at two very different locations, is a source of confusion at the moment. Voyager 2 also made some observations that don't square up with a sharp boundary, at least not what we'd expect. The biggest of these is the magnetic field measurements inside and outside the bubble. Astronomers expected the direction of the magnetic field would be very different between the two. Yet, when Voyager 2 crossed this thin surface, there was essentially no change in the direction of the field. This is something Voyager 1 observed as well. At the same time, the magnetic field observations on Voyager 2 suggest it found a thinner and simpler heliopause, filled with less energetic particles than what Voyager 1 crossed. Again, all this data taken together raises more questions than it can answer. It is well known that the Sun consistently spews out shock waves of plasma called coronal mass ejections, which help shape the rest of the solar system. Turns out the Sun's impact goes beyond its own borders. The new Voyager 2 data, like the Voyager 1 data before it, shows how CMEs propagate past the heliopause and lower the number of cosmic rays beyond the bubble. This is somewhat similar to what you might find in the galaxy. Supernovae send shockwaves out into the galaxy as well, stirring the interstellar medium, albeit at a much more intense scale than CMEs. Most astronomers believe that the formation of the solar system was triggered by an interstellar shockwave from a supernova. If we think about the potential for cosmic rays to promote biological mutations in life on Earth, these findings lend support to the area that the Sun could also influence the evolution of living things on extraterrestrial worlds, in this planetary system and elsewhere. Both Voyagers have operated far longer than mission planners expected and are the only spacecraft to collect data in interstellar space. Each spacecraft produces about 4 fewer watts of electrical power a year, limiting the number of systems the craft can run. The mission engineering team has switched off various subsystems and heaters to reserve power for science instruments and critical systems. No science instruments have been turned off yet because of the diminishing power, and the Voyager team is working to keep the 2 spacecraft operating and returning unique science beyond 2025. Scientists believe that solving these puzzles will require a better view of the heliosphere as a whole. Voyager 1 exited near the heliosphere's leading edge, where it collided with the interstellar medium, and Voyager 2 exited along its left flank. We have no data on the heliosphere's wake, so its overall shape remains a mystery. The interstellar medium's pressure might keep the heliosphere roughly spherical, but it's also possible that it has a tail, like a comet, or that it is shaped like a croissant. But while other spacecraft are currently outward bound, they won't be able to return data from the heliopause. NASA's New Horizons spacecraft is zooming out of the solar system at more than 31,000 miles an hour, and when it runs out of power in the 2030s, it'll fall silent more than 1 billion miles short of the heliosphere's outer edge. That's why Voyager scientists and others are calling for a follow-up interstellar probe. The current goal is a 50-year, multi-generation mission that explores the outer solar system on its way into unexplored regions beyond the solar wind, but nothing new is in the works so far. Despite these stunning discoveries, we all know that nothing lasts forever, and the same is true for both the Voyager crafts. When the two Voyagers were launched, the space age was only 20 years old. It was hard to know at that time that anything could last for over 40 years. Scientists believe that the observations of the heliopause are part of the last hurrah for both spacecraft. Each probe is powered by radioisotope thermoelectric generators heated by plutonium-238. That material is undergoing natural decay. NASA states that in another 5 years or so, the probes may not have enough power to have any scientific instruments on any longer. Until then, the two missions will continue to learn how the sun's heliosphere interacts with the interstellar medium and give us clues about other star systems. What the mission helps us learn about the heliosphere will help us learn more about the atmospheres of other stars. Though NASA continues to monitor, communicate with, and collect data from both Voyager probes, converting this data into useful scientific insights is largely the responsibility of scientists based at different institutions throughout the U.S. There are currently no plans for a successor to the Voyager program, but the success of the missions and the questions they raise will undoubtedly inspire these scientists and engineers to come up with new proposals to study the heliosphere and beyond. The latest reports state that the engineering team with NASA's Voyager 1 spacecraft is trying to solve a mystery. The Interstellar Explorer is operating normally, receiving and executing commands from Earth, along with gathering and returning science data. But readouts from the probe's attitude, articulation, and control system don't reflect what's actually happening on board. The AACS controls the 45-year-old spacecraft's orientation. Among other tasks, it keeps Voyager 1's high-gain antenna pointed precisely at Earth, enabling it to send data home. All signs suggest the AACS is still working, but the telemetry data it's returning is invalid. For instance, the data may appear to be randomly generated or does not reflect any possible state the AACS could be in. The issue hasn't triggered any onboard fault protection systems, which are designed to put the spacecraft into safe mode, a state where only essential operations are carried out, giving engineers time to diagnose an issue. Voyager 1 signal hasn't weakened either, which suggests the high-gain antenna remains in its prescribed orientation with Earth. The team will continue to monitor the signal closely as they continue to determine whether the invalid data is coming directly from the AACS or another system involved in producing and sending telemetry data. Until the nature of the issue is better understood, the team cannot anticipate whether this might affect how long the spacecraft can collect and transmit science data. Voyager 1 is currently 14.5 billion miles from Earth, and it takes light 20 hours and 33 minutes to travel that difference. That means it takes roughly 2 days to send a message to Voyager 1 and get a response, a delay the mission team is well accustomed to. Scientists are hard at work trying to explain this new mystery and believe that the data may be a result of the craft deteriorating due to age. The spacecraft are both almost 45 years old, which is far beyond what the mission planners anticipated. They are also in interstellar space, which is a high radiation environment that no spacecraft have flown in before. While this is a big challenge for the team, scientists believe if a solution to the AACS issue exists, they will find it. Another possibility is that the team may not find the source of the anomaly and will instead adapt to it. If they do find the source, they may be able to solve the issue through software changes or potentially by using one of the spacecraft's redundant hardware systems. It wouldn't be the first time the Voyager team has relied on backup hardware. In 2017, Voyager 1's primary thrusters showed signs of degradation. So, engineers switched to another set of thrusters that had originally been used during the spacecraft's planetary encounters. Those thrusters worked despite having been unused for 37 years. Voyager 1's twin, Voyager 2, continues to operate normally. Launched in 1977, both Voyagers have operated far longer than mission planners expected and are the only spacecraft to collect data in interstellar space. Each spacecraft produces about 4 fewer watts of electrical power a year, limiting the number of systems the craft can run. The mission engineering team has switched off various subsystems and heaters to reserve power for science instruments and critical systems. No science instruments have been turned off yet as a result of the diminishing power, and the Voyager team is working to keep the two spacecraft operating and returning unique science beyond 2025. While the engineers continue to work at solving the mystery that Voyager 1 has presented them, the mission scientists will continue to make the most of the data coming down from the spacecraft's unique vantage point.